Okay, guys, Math 6620. I'm going to get into more regression. In the previous videos, we've looked at how to examine relationships using correlation, different types of correlation between two variables. We're going to move into regression, which, in my opinion, probably other than logistic regression, I think multiple regression methods and techniques are probably is commonly used in ed research as anything, again, other than probably logistic regression. Now, I want to get into just simple linear regression and go over some just real basics. But guys, remember that what we looked at previously is that the deviation in our model is pretty easy to describe. It's just the sum of the observed values minus the model values, quantity squared. So our observed values are our y sub i's, and our predicted values are the y hat sub i's. And I kind of introduced that to you ad nauseum in the at least two of the previous three videos. So what I want to do now is I want to kind of switch gears, and I want to focus on creating a model that can be used to predict a quantitative variable, a y, from, for now at least, a quantitative predictor, x. So guys, we're going to use x to predict a y where both of these are quantitative. Now, first thing I want to do here is I want to focus my attention on three measurements, and they're all called a particular type of sum of squares. And I think the best way to visualize this is to just construct a scatter plot between x and y, but keep it simple. So let's just have, for example, four measurements that we have collected, and let's focus on this point right here. Now, if we draw the line down, we can see that this point came from a particular x sub I, and it has a particular y sub I value. So the observed data point is x sub I, y sub I. Guys, my Fitbit is actually going off, so it's kind of annoying. Now, we also can look at our y's, and we can imagine this is probably going to be a little bit low, but I want to draw the mean of the y's here just to make a point. So for this particular value of x, we can come up to this point. That point is, of course, the mean of y. This point is the predicted value, so it's the y sub I, y hat sub I, if you will. And this point, of course, is the observed value. Now, if we look at the difference, the distance from here to here to here is the observed y down to the mean value. This is referred to as our total sum of squares. Our total sum of squares can be partitioned into two parts to sum up to get the total sum of squares. They can be partitioned into what we call the sum of squares for the error. And then this part right here is the sum of squares for our model, or our model sum of squares. So guys, the total, I'll tell you what, let me start a new sheet of paper. The total sum of squares is equal to the sum from I equal 1 to n of our observed values minus the mean squared. Our, I'm just going to call it residual sum of squares. By far the easiest one to remember, because it's just the difference between the observed and the predicted. And of course we have our model sum of squares, which is the sum from I equal 1 to n of our y hat sub i's minus our mean squared. So guys, if we think about it, the total sum of squares is just the difference between the observed and the mean. The residual sum of squares is the difference between the observed and the regression line. And the model sum of squares is the difference between the mean and the regression line. So the regression line away from the observed, the regression line away from the mean. And guys, our total sum of squares will be equal to the residual sum of squares plus the model sum of squares. Now, what we typically want to do once we calculate these sum of squares is we will want to create an ANOVA table. And what the ANOVA table does, it gives us kind of a diagnostic for our regression model, an overall diagnostic, along with R squares and adjusted R squares and a chi-chi, what's an AIC? It's just another measure we'll get into, which is more appropriate for comparing models that have multiple predictors. But anyway, we'll get into that in just a second, or probably not until the next video, actually. But anyway, guys, we'll have a sum of squares column, and we'll have our model sum of squares, and we'll have our error sum of squares, and then we'll have our total sum of squares. The next thing we'll have is we'll have a column for our degrees of freedom. Now, not all technology presents these in the sequence that I'm presenting here. Sometimes you'll see the degrees of freedom first. But anyway, it's same stuff, 601, half a dozen of the other. Guys, it turns out that the degrees of freedom for the model are just the number of predictors, which I will call K. The degrees of freedom for the error are our sample size minus the number of predictors, minus 1, and then our total degrees of freedom are just n minus 1. Now all of this leads into what we call our mean square term. So if we take our sum of squares for the model divided by the sum of squares degrees of freedom, then we get the mean square for the model. If we take the sum of squares for the error divided by the degrees of freedom for the sum of squares for the error, we should have a model in there someplace and an error in there someplace. We get our mean square. Now, I can take my sum of squares model and add my error sum of squares, and I will get my total sum of squares. I can take my degrees of freedom and add the degrees of freedom for the model and add the degrees of freedom for the error, and I will get the degrees of freedom for the total. However, the mean square is not additive, so we typically leave that part of the table blank. All right. So next thing we do is we get into our F statistic, and our F statistic is just the mean square for the model divided by the mean square for our error term. And then we end up getting a p-value. Now essentially what tells us in the end, if we get a p-value, if we get a p-value less than 5 using that industry standard of 0.05, it just tells us that our model is better for predicting y. Our model using x in this case, we'll get into multiple regression later, but for right now our model using x to predict y is better than just using the mean of y. All right, so let's look at an example. I think it'll be worth running through an example here. So I had a data set. We used a few videos ago, and it's a small data set, and it's easy to manipulate. So what I would like to do is I would like to create the ANOVA table by hand from this data set. So guys, essentially what do I need? I need the sum of squares for my, well, I'll tell you what, let's do this different. I want my model, I want my error, and I want my total. So I want the sum of squares, I want the degrees of freedom, I want the mean square, I want to calculate my F statistic, and I want to calculate my p-value. All right, and I want to do this by hand. But typically we wouldn't do this by hand. Typically we would, and it's something I'll do later on. We'll put it into R and we'll calculate these values. But I think it's worth running through at least one time to see how these things are calculated. Now, we know because these things are additive, if we take the sum squares for the model, sum squares for the error, if we get 2 out of 3, we can find the other one. So I think what I want to do here is I just want to look at the difference between the predicted and the mean. So first thing I'm going to do is I'm going to create the sum of squares for the model. You guys remember, what is that? It's just the sum of the predicted values minus the mean. You know, actually, I don't want to do that. Yeah, I guess it's as broad as it is long, isn't it? So, guys, what I want to do is I want to get into R, and I've already got it up here. So, well, maybe it wants me to get rid of this first. Some reason. All right, so let's just enter some data. Sorry, I can't talk and type or I'll mess up. Now, if we want to keep start a data frame, set up a data frame, we could. There's really not much need for it, but you know, some people just like to do that. You know, I don't know. All right, so now we have our x and our y in a data frame. So I want to create the predicted values minus the mean and square. So guys, the first thing I'd have to do is create my model. So I'm going to just call this model, and I'm going to look at the linear model y predicted from x. So very simple model. Now, what I can do is to get my predicted values, there's a command that says fitted. So these are going to be my predicted values. So essentially what I need to do is take each one of those and subtract it from the mean. So I'm going to call this sum of squares model. So I'm going to take the fitted for the model minus the mean of my y's, and then I want to square this. So it's going to give me a list. Now SSM is going to give me a list, so what I want to do is I want to find the sum of SSM. So I know that my sum of squares for the model is 25.804. So going back here, I know that 25.804 was the sum of squares for the model. Now, hopefully you guys can see that. I know it's kind of small. So the next thing I think I'd want to do is I'd want to get into maybe, I don't know, sum of squares for the error. So let's think about what the sum of squares for the error term is. It's just the difference between the observed y's and the predicted y's. Well, my observed y's are just y, minus my predicted y's are the fitted values, and then I can square that, and I get the sum of my y values minus the observed values minus the predicted values. All right. So now I want to go sum of squares. So I want to sum up those values, and I get 8.196. 8.196. All right, I don't want to forget that. So gang, my error is 8.196. So guys, let me grab a calculator. So I know that the sum of squares for the total will be the sum of these two. Don't really need to add these up. Didn't really have much practical consequence, but be something that that we can do. All right. So the sum squares for the total would be 34. Now, next thing we need to do is we need to get into our degrees of freedom. And in this situation, we have one predictor. Now, we have a sample size of 5, right? So 5 minus 1, predictor, minus 1, degree of freedom. So we have our error term has degree of freedom 3. And our total is just the total sample size 5 minus 1 equals 4. Now, my mean square term is going to be found by taking the sum squares of the model divided by its degrees of freedom. And then we'll take the error sum of squares divided by its degrees of freedom. So that's just 8.196 divided by 3. So I get 2.732. Now, to get my F statistic, I take the mean square for the model divided by the mean square for the error. So I take 25.804 divided by 2.732. So I get 9.445. Now, this 9.445, if I want to calculate the p-value, what I'm going to do is I'm going to examine the F distribution, degree of freedom 1, 3. And I'm going to look at the F value of 9.445. And the p-value is the area to the right of the F statistic, test statistic here. So guys, that's going to be really easy to do with R. So I'm going to go 1 minus PF, which gives me the probability using the F distribution. These are degrees of freedom 1, 3, and I want the area 9.445. Now, guys, this PF always gives you the area below, but the way that the p-value is calculated in F distribution, I need the area above. So since the area under any probability distribution curve is 1, it should make sense why we can we subtract that from 1. So guys, my p-value is 0.434. So we do not have statistical significance, which means that my model is no better than just using the mean value for y to predict the value for each x. So guys, what I can do now is I can replicate what I just, or at least show you on R what we just did. So replicate it using technology. So guys, I can just type ANOVA for my model. And guys, you're going to see a whole lot of information that you've seen before. All right, so our degrees of freedom. Now, one thing that R doesn't do, it doesn't give you a total. But again, remember, the only two totals that are appropriate would be the total degrees of freedom, the total sum of squares. The mean square total would be blank because it is not additive. So our F value is 9.44. Okay, I have a p-value of 0.0543. What did I do wrong? 9.445. Okay, what's going on, boys and girls? The degrees of freedom are... Where did I go? Where did I go wrong? Oh, I think I know what I did. Shoot. I have to put the 9.445 first, and then I have to put the degrees of freedom. Yeah, that's what it is. So, first mistake I've ever made, and you guys got to see it firsthand. Don't you feel privileged? I wish it was the first mistake I've ever made. So guys, again, put your test statistic first, and then your degrees of freedom come second. All right, so you can see now that our probability lines up. It's not statistically significant at the 0.05 level. It is significant at the 0.10 level, but typically we, use that threshold of 0.05 as we've talked about ad nauseum. Now, a couple of other things that we want to take a look at. I want to keep this video kind of short, so let's try to attempt to do that. A couple of other things that we want to look at from our ANOVA table is we want to look at our R squared. That's hard for a Kentuckian to say, and it's just the ratio of the sum of squares for the model over the sum of squares for our total. Now, our sum of squares for our model was 25.804. Sum of squares for our total was 34. So looks like to me, if I didn't make a typo, that's 0.759. So what we can say here is we can say that 75.9% of the variance in Y is explained by the regression on X. Now when I look at that, I kind of look at it as the glass half empty. So I see that there's approximately 24%, 24.1% to be specific, of the variance in Y that's not explained by the regression on X. But nevertheless, you know, when you get an R squared somewhere around 80%, you got something worth talking about. Now, since we only have one predictor, and it's the only time that this actually works when we have one predictor, we can find R by taking the square root of 0.759 to get 0.87. So that's the Pearson correlation coefficient. So the R value is 0.87, which tells us we have a fairly strong linear relationship between X and Y. Now, something else you're going to see a lot of, you're going to see these adjusted R squared. Now, what happens with adjusted R squared is really in response to a characteristic of R squared that's extremely annoying. And that characteristic is that R squared will always increase when you add an additional variable. Even if your variable is not any good, R squared will artificially increase. So therefore, we have a motivation to find something else that's a little bit more stable. Now, one of those is an adjusted R squared. And guys, your adjusted R squared is always going to be less than your R squared, and it isn't artificially inflated by adding additional variables. Now, another one that we take a look at is called the AIC. And the AIC is the, I never feel like I pronounced this correctly. Akaiki? Akayaki. Okay, I think I got it right. Akayaki. And that's just information criterion. If my PhD required me to say Akayaki very often, I don't know if I would have finished successfully. But anyway, he's a very well-known statistician from Japan. I think he passed away probably around early 2010. I don't know. I finished my PhD in 2002. Yeah, I think about 2010 is when he passed away. But anyway, what this does for us, it gives us another measurement similar to the adjusted R squared, and it's very easy to manipulate. It's just the n times the natural log of the sum of squares, error divided by n, plus 2k. Now guys, that plus 2k tends to be the part that gets all the attention because it tends to be kind of the stabilizing factor. Now, unlike many measurements in statistics, a smaller AIC indicates a better fit, and a larger AIC indicates a worst? That's horrible. A bad fit. Okay, a worse fit. I'm kind of sidetracked here, but that's one of those things. And something you got to remember too about AIC, it's really only helpful when comparing models on the same variables. So, if I wanted to compare from the same data set, let's say I wanted to predict Y from X1 and X2, and I wanted to do another model again on the same data set using X1 and X3, then I can compare AICs and see which model gives me the better fit. It would be the one with the smaller AIC. But if I jump from data set to data set, really comparing AICs doesn't do much for you or much for us. And it's going to be really, we're going to get into stepwise regression, backward elimination. We might get into some hierarchical regression, but we're going to get into different selection methods where the AIC comparison is going to be very, very beneficial. All right, boys and girls, I'm going to call it a day. Let's end the video and getting ready to put up another one. So take care.